In the previous lecture, we saw how the first stars were created. Now, with the appearance of stars, our universe is already much more interesting than it was. We saw how, with remarkably limited ingredients, gravity managed to cook up these new complex things, stars. And as we did so, as stars were created, we actually moved from cosmology, that's the discipline that studies the universe as a whole, to physics and astronomy, disciplines that study some of the first complex objects that were made in the universe, such as stars and atoms. In fact, you'll notice that when we cross in this course from one level of complexity to another, we're often going to be crossing also from one scholarly discipline to another. So now, our universe is dotted with billions of tiny hotspots that pour energy into the cold of surrounding space. But how far can you go with this? Could you make even more forms of complexity with just the existing elements, with hydrogen, helium, gravity, other forms of energy, and stars? It's hard to see how. We'll see, in fact, that all later forms of complexity, or at least all those that are significant to human beings, depend on the existence of a larger palette of chemical elements. These make it possible to create a greater variety of material elements, of stuff, of substances, if you like. And using these, it's possible to combine them so as to create entities that have new emergent properties. And one of these emergent properties will eventually turn out to be life itself. So the creation of new stuff, new chemical elements, takes us from the physical level of complexity, from the level of atoms and stars, to a new level which we'll call the chemical level of complexity. So as we cross from the disciplines of astronomy and physics to that of chemistry, we find ourselves ready for the new levels of complexity that eventually will form life and you and me. So that's our central question for this lecture. How do you create new chemical elements? Before we can really answer that question, we need a very clear idea of what we mean by chemical elements. The chemical elements are the 92 most elementary forms of matter, ranging from hydrogen, with just one proton in its nucleus, to uranium, with 92. There are, in fact, other elements that have more protons than uranium in their nuclei. They can be created artificially, and some may have been created occasionally by natural processes, but they're so unstable that they soon break down. They're known as the transuranic elements. Modern understanding of chemical elements really goes back to the work of the Russian chemist Dmitry Mendeleev, whose dates are 1834 to 1907. Mendeleev was born in 1834 in Tobolsk in Siberia. In 1869, now a young professor at St. Petersburg University, Mendeleev did something for chemistry and for chemical elements that was rather similar to what Hertzsprung and Russell had done for stars. What he did was he arranged them in a new way that revealed new and hitherto unsuspected features. He produced a list of the chemical elements that were known in his time, and he arranged them so as to reveal some striking and unexpected new regularities that no one had seen clearly before. He arranged them first in rows. He arranged them by atomic weight, so they're getting heavier and heavier and heavier, row by row. Now, we now know that it would have been slightly more precise to order them by atomic number, that is to say, the number of protons in the nucleus. For example, hydrogen has one atom, has one proton in its nucleus, carbon has 6, oxygen has 8, silver has 47, gold has 79, and uranium 92. These are their atomic numbers, the numbers of protons in their nuclei. In all but a few cases, however, these two rankings, ranking by atomic weight and by atomic number, coincide, which is why Mendeleev's version of the table worked as well as it did. Now, that was the first arrangement, horizontally by atomic weight, and nowadays by atomic number. But the really interesting information was found in the vertical columns of his table. He found that the elements known in his time could be arranged in such a way that the vertical columns contained elements with similar features, features such as differing degrees of chemical reactivity. And he also showed something else. These features recurred at surprisingly regular intervals. At first they recurred every 8 elements, then every 18, and finally every 32 elements. So striking were these patterns that Mendeleev was eventually able to guess at the position and even some of the chemical qualities of elements that had not yet been discovered. For example, he discovered that an undiscovered element ought to lie somewhere between calcium and titanium, and he listed some of its properties. That element, which came to be known as scandium, promptly turned up in about 1879, along with the appropriate chemical properties. Now, when a scientist manages to make predictions like this is one of the most powerful forms of proof that can exist. So this prediction was a sign of the power of the arrangement of elements that Mendeleev had put together. Today, with a much fuller understanding of the nature of chemical elements and how they work, these patterns can be seen even more clearly. For example, the so-called noble or inert gases consist of helium, whose atomic number is 2, neon, whose atomic number is 10. You notice the gap of 8 between them. Argon, 18, another 8. Krypton, 36. Now we get a gap of 18. Xenon, 34, another gap of 18. Then radon, atomic number 86. All of these appear in the last column of modern versions of Mendeleev's table. And as we've seen, the intervals between them are 8, 8, 18, 18, and 32. And you'll find similar intervals in other vertical columns. For example, the so-called halogens are extremely reactive elements. They include fluorine, number 9, chlorine, 17, bromine, 35, iodine, 53, and astatine, 85. Though he was struck by these intervals, Mendeleev himself couldn't explain them. Partly because doing so required understanding of the role of the electron in atoms, and the electron had not yet been discovered when he devised his table. We now know that these periods depend on the way electrons were arranged in the outer shells of atoms. In fact, the number of electrons in the outer shell of an atom determines many aspects of its chemical behavior, including its liability to react and the way it reacts with different elements. If, like the noble gases, you have a complete outer shell, then you're not likely to need to react much with other elements, and that explains why the noble gases are inert. Mendeleev's table is now known as the periodic table of the elements, and it's been described as the most elegant organizational chart ever devised. It gave shape to our modern understanding of chemical elements, and the existence of chemical elements is crucial to the existence of planets, living organisms, and ourselves. So they're the key to the third threshold of complexity in our course. So back to the question of how they were made. How were they made in a universe that consisted entirely of hydrogen and helium? Mendeleev himself had no clue, nor would anyone else until about the middle of the 20th century, when astronomers finally managed to get a much better understanding of the life cycle of stars, because stars turn out to be the key to this process. So, how were the elements created? Now, the first thing to note is that most elements were not formed in the Big Bang. And there's a reason for this. The reason is because in the initial split second of the Big Bang, temperatures were just far too high for protons to lock together, to form the multi-proton nuclei that you need for more complex elements. Then, when temperatures had fallen low enough for protons to combine to form helium with 2 protons, they were now too low to form other elements. So it's as if things moved far too fast in the first second or two of the Big Bang to form any other elements apart from hydrogen with 1 proton in its nucleus and helium with 2, and tiny amounts of lithium, atomic number 3, and beryllium, atomic number 4. So within minutes of the Big Bang, temperatures were too low to form elements heavier than hydrogen and helium. And that explains why most of the universe today consists of hydrogen and helium. And those were the 2 elements created in the Big Bang. So, if the universe was too cold to jam together atoms to form more complicated elements, where could they form? We need to look somewhere where remarkably high temperatures could be generated. And of course, stars are the place to look. Temperatures high enough for the creation of further elements would not be recreated in the universe until the appearance of stars. But to understand how stars created temperatures high enough to synthesize heavier elements, we need to understand something about their life cycles. So let's return to the Hertzsprung-Russell diagram, the HR diagram. We saw that this, a bit like Mendeleev's table, summarizes a large amount of information about different types of stars. The diagram is a scatter graph. It ranks stars according to 2 types of measurement. The first parameter is their brightness, or the amount of light they emit. And this is often given as a multiple of the sun's brightness. In most forms of the HR diagram, this is measured on the vertical axis. And this means that stars that are emitting more light appear higher up the graph than cooler stars. In effect, a star's brightness tells us its real mass, the amount of matter it contains, because a large star generates more density and higher temperatures. The second parameter on the HR diagram is a star's surface temperature, which can be different than its overall temperature. This can often be estimated from the star's color. By and large, the bluest stars are the hottest, and red stars are cooler. Surface temperature is normally plotted on the horizontal axis, so that bluer stars with higher surface temperatures appear to the left of the graph, and redder stars to the right. So just to recapitulate, the hottest stars appear higher up on the graph. Those with the hotter surface temperatures appear on the left-hand side of the graph. Now, when you look at an HR diagram, you'll see that there's a broad band of stars that appear on a narrow diagonal band, which is called the main sequence. And this runs from the top left, where we find stars that are large, bright, and very hot, and they tend to be bluish, to the bottom right, where we find stars that are smaller, less bright, less hot, and reddish. All stars on the main sequence are normal, mature stars. The temperatures in their core are hot enough to fuse hydrogen into helium, at least 10 million degrees, but not high enough to create elements with higher atomic numbers. So all the stars on the main sequence are doing what stars spend most of their time doing throughout most of their lives. Their job, basically, is turning hydrogen into helium. And that's what they spend most of their lives doing. So that's the main sequence. What this band, the main sequence, seems to be telling us is that for most of their lives, overall brightness, total mass, and surface brightness are closely correlated. That's why you get this neat line. Now, why does a star appear on a particular part of the main sequence? A particular star will appear at a particular place in the main sequence, and it'll stay there for most of its life. Its position depends on one factor, its mass. And that essentially means the amount of stuff that went into making the star. Why is this? Well, small stars generate less pressure at the center, and they burn at lower temperatures. So they burn their nuclear fuel slowly, and they may live for billions of years. These appear at the bottom right of the main sequence. They're cooler and they're smaller. Our sun is in the middle of the main sequence. It's quite large and it's quite bright. It's probably going to last for about 9 billion years, which we'll see means that it's about halfway through its life. Stars that are more than about 10 times larger than our own sun create much more pressure at their centres, much higher temperatures, and they burn through their fuel much faster. The biggest stars, such as Rigel in Orion, shine with a bluish light, and they appear at the top left of the main sequence. They may live for just 1 million years or so because they gobble up their fuel so voraciously. But note once again that none of these stars on the main sequence can generate temperatures high enough to create elements with atomic numbers higher than 2, that is to say helium. All they can do is turn hydrogen into helium. Things get really interesting when stars approach the end of their lives. So now we need to undertake the slightly ghoulish task of surveying what stars do in their death agonies. The death of a star begins when it runs out of the hydrogen that's kept it running for most of its life. At this point, you'll see the star sort of wandering away from the main sequence on the HR diagram. It starts going a bit mad, frankly. But where it goes depends, once more, on its mass. Now let's begin with our sun and what is likely to happen to our sun. When it's used up all the hydrogen in its core, the core will cool and collapse. So suddenly the furnace that's held the sun up for 4.5 billion years so far will suddenly splutter out, and it'll stop propping the star up. Remember, star formation began with gravity collapsing a cloud of matter in on itself. Now, without the furnace created by fusion, that collapse can continue. But the collapse itself compresses the star's center, creates such pressures that its temperature starts to rise again. And it'll rise quite quickly to temperatures much higher than those at which hydrogen fused into helium. Eventually, at about 100 million degrees, about 10 times higher than the minimum temperature needed to fuse hydrogen into helium, helium atoms will start fusing to form carbon. So now the star can burn helium. Now for the first time, remember, stars are starting to build larger chemical elements because now we've got the high temperatures we need. At this point, you have a new furnace at the center of the sun. The sun will start to expand again. It'll reach beyond the orbit of Mercury, and it'll turn into a red giant, like Aldebaran in the constellation of Taurus. As it burns helium, it will move away from the main sequence to the upper right of the HR diagram. This is because it'll get brighter. It'll get brighter because helium burns at higher temperatures than hydrogen. So this moves it up the graph. But it will also get redder. And this is because hydrogen continues to burn in its upper layers, lowering its surface temperature. So this places it over to the right of the graph, towards the end where surface temperatures are cooler. So now you'll find it in the upper right-hand corner of the HR diagram, along with other red giants, such as Aldebaran. Now, it's going to burn through its helium much more quickly than it burned through its hydrogen. It's burning at a much higher temperature, remember. Once all the helium is burnt up, the process is going to repeat itself. Our sun will collapse again, temperatures will rise in the center, and it will expand again, until this time it includes the orbits of Mars and Earth, and it'll vaporize both planets as it does so. So any unfortunate descendants of ours that are still living on Earth will be toast. The sun itself will have become a red supergiant, like Betelgeuse in the constellation of Orion. Incidentally, if you haven't seen it, look for it at a northern corner of Orion, diagonally opposite Rigel. It really is red. Now, our sun is too small to take these processes further. It cannot create temperatures hot enough to start fusing carbon and further elements. Eventually, it'll shed its outer layer, and it'll collapse around its carbon core, and it'll turn into a white dwarf about the size of the Earth. Now, though it's still quite hot, it has no internal furnace, and it'll gradually burn out. Sirius B, the companion star to Sirius A, which is the brightest star in the night sky, is a white dwarf. Our sun at that point will move swiftly below the main sequence of the HR diagram towards the bottom left of the diagram. It'll become smaller and less bright, but with a high surface temperature. Then, over billions of years, it will cool until eventually any surviving astronomers will start calling it a black dwarf. And now it'll just sit there, a mere cinder, completely invisible, doing nothing for countless billions of years, side by side with an increasing number of other dead stars, until eventually the universe as a whole will slowly turn into a vast, ghostly cemetery of dead stars. So that's the fate of our sun. Now, what about smaller stars? Stars that are smaller than our sun will burn much longer because they burn more slowly. When they run out of fuel, some will simply collapse into white dwarfs, or they may briefly burn helium and then collapse into a white dwarf. So this is not terribly exciting. What is much more interesting is the death of really large stars. Stars much larger than our sun. Now, what happens when they run out of hydrogen? At first, the story is a bit like our sun. They start burning helium, and when that's gone, temperatures will still be high enough for them to burn their way through carbon and a number of other elements, including oxygen and silicon, until eventually they start producing large amounts of iron in their cores. And the temperature at their core reaches 4 billion degrees. Now, these processes start speeding up. As temperatures rise, things start happening faster and faster, and things get more and more dramatic. Here's a wonderful description of what happens from Cesare Emiliani's wonderful scientific companion. This is how he describes this phase. A star 25 times more massive than the sun will exhaust the hydrogen in its core in a few million years. And as the core continues to contract and the temperature continues to rise, it will burn carbon for 600 years, oxygen for 6 months, and silicon for just 1 day. During all of this, iron, the final product of these processes, is building up in the center. But iron marks the end of the road. No star can go further than iron. So eventually you've got a core full of iron and the furnace shuts down. The star will then collapse catastrophically in just a second or two before exploding. Most of its mass will be hurled into space. And this, of course, is a supernova. At this point, the supernova may shine with the brilliance of an entire galaxy. The Crab Nebula, incidentally, is the remnant of a supernova that was observed by Chinese astronomers in 1054. So it's thrown out most of its outer layers. Its core will then collapse, possibly into a neutron star. Now, a neutron star is a ball of matter so dense that all atoms are crushed into their nucleus. The electrons that normally orbit way away from the nucleus are crushed right into the center. So it's like nuclei next to each other. It's been estimated that a spoonful of matter from a neutron star would weigh about 90 billion kilograms. It might have the mass of the Earth, but it would be in a ball just 30 to 40 miles wide, rotating many times a second. As they spin, pulsars emit regular flashes of energy which can sometimes be detected on Earth, which is why such stars are known as pulsars. If the supernova is even bigger, if what's left of the star is even bigger, the collapse will go further than a neutron star and create a black hole. Now, a black hole, I wish we could spend more time, and I wish I had the expertise to talk more about black holes, but a black hole basically is an object so dense that not even light can escape its gravitational pull. A black hole, as a result, can have hardly any further communication with the rest of the universe. It's as if it had got almost completely pinched off from the universe. So, as we'll see, and as Stephen Hawking showed, not completely pinched off. Now, it's in the extreme temperatures of a supernova, much higher than those in the center even of the largest collapsing stars, that finally the remaining elements of the periodic table can be manufactured, and they can be manufactured in just a few seconds, all the way through gold and lead to uranium. So in summary, it's taken 3 steps to create the chemical elements from which you and I are constructed. Hydrogen and helium, the simplest atoms in the periodic table, were created during the Big Bang. And that's why they are, although it's only recently been realized that this was so, that's why they are by far the most common elements in the universe. In the early universe, hydrogen made up about 75% of the universe, and helium about 24%. That leaves just 1% for everything else. In their death throes, medium to large stars create elements such as carbon with 6 protons, nitrogen with 7, oxygen with 8, and silicon with 14, up to iron with 26 protons. So here's the second stage. In the dying phases of large stars, you cook these successive elements up to iron. And that explains why these elements up to number 26 tend to be much more common than later elements in the periodic table. So as these dying large stars throw off their outer layers, these elements are scattered through space. So, though not as common as hydrogen and helium, these elements are much more common than later elements. That's the second phase. And then the third phase. All remaining elements are manufactured and scattered through the universe in supernova explosions. Now, think what this means. If, like me, you're wearing a gold ring, or if you're wearing silver jewelry, look at it. The silver or gold was made in a supernova explosion. It's probably been around for billions of years, and it's on very, very temporary loan to you. And the same goes for all the elements in your body. At least all the elements above iron. So I hope this makes it clear why the life and death of stars is a topic that should be very dear to us. Without dying stars, we could not possibly exist. So let's summarize what we know about the third of our major thresholds. The first stars represented a new level of complexity in the universe, but they also provided the energy flows and the chemical ingredients needed to make even more complex entities such as our Earth. So without stars, it would have been impossible to create new levels of complexity such as planets or you and me. They prepared the way for new levels of complexity with new emergent properties. And those properties are sufficiently different from those studied by astronomy and physics that they are the domain of a new scholarly discipline, chemistry. And this is what we'll see repeatedly. New levels of complexity and new emergent properties give rise to new scholarly disciplines, from cosmology to chemistry to geology, the next threshold, then to biology, and finally, human history. I hope you're beginning to get a sense of the capacity of big history to unify knowledge. Because what we've seen here is one of the many virtues of big history, which is that it can help us see better both the links and the differences between these different domains of complexity. In the next lecture, we'll start looking at some of the new things that could be constructed using this vastly expanded palette of chemical elements that was cooked up inside stars. And the first objects we'll look at are planets, including our own Earth. Thank you. New stuff, new chemical elements, takes us from the physical level of complexity, from the level of atoms and stars, to a new level which we'll call the chemical level of complexity. So as we cross from the disciplines of astronomy and physics to that of chemistry, we find ourselves ready for the new levels of complexity that eventually will form life and you and me. So that's our central question for this lecture. How do you create new chemical elements? Before we can really answer that question, we need a very clear idea of what we mean by chemical elements. The chemical elements are the 92 most elementary forms of matter, ranging from hydrogen, with just one proton in its nucleus, to uranium, with 92. There are, in fact, other elements that have more protons than uranium in their nuclei. They can be created artificially, and some may have been created occasionally by natural processes, but they're so unstable that they soon break down. They're known as the transuranic elements. Modern understanding of chemical elements really goes back to the work of the Russian chemist Dmitry Mendeleev, whose dates are 1834 to 1907. Mendeleev was born in 1834 in Tobolsk in Siberia. In 1869, as stars were created, we actually moved from cosmology, that's the discipline that studies the universe as a whole, to physics and astronomy, disciplines that study some of the first complex objects that were made in the universe, such as stars and atoms. In fact, you'll notice that when we cross in this course from one level of complexity to another, we're often going to be crossing also from one scholarly discipline to another. So now, our universe is dotted with billions of tiny hotspots that pour energy into the cold of surrounding space. But how far can you go with this? Could you make even more forms of complexity? In the previous lecture, we saw how the first stars were created. Now, with the appearance of stars, our universe is already much more interesting than it was. We saw how, with remarkably limited ingredients, gravity managed to cook up these new complex things, stars. And as we did so, with just the existing elements, with hydrogen, helium, gravity, other forms of energy, and stars, it's hard to see how. We'll see, in fact, that all later forms of complexity, or at least all those that are significant to human beings, depend on the existence of a larger palette of chemical elements. These make it possible to create a greater variety of material elements, of stuff, of substances, if you like. And using these, it's possible to combine them so as to create entities that have new emergent properties. And one of these emergent properties will eventually turn out to be life itself. So the creation of new